Hi everyone, I'm Daniel Rossano, and I am going to talk to you all today about using a check cohomology to find loops and gaps in data sets. So what is check cohomology? That's a pretty good place to start since it's not something you hear very often. Well, check cohomology is a kind of topological data analysis. Now, topological data analysis is just an area of applied math where you take concepts, typically from algebraic topology, things like homology, or in this case, cohomology, and you apply them to data sets in the real world. Now, there's also a pure math theoretical reason for studying check cohomology. It's useful for classifying the structure of manifolds. And we can, in practical examples, utilize this for data sets as well. This also ties back into why it's so helpful for topological data analysis. Check cohomology can help us identify holes or gaps in data sets. One thing to keep in mind is that there's a lot more to the story here. There's a lot of topology behind this concept, and we're going to have to gloss over that just so we can wrap this all up in a reasonable amount of time. But we're only working with practical examples here, so we can actually explain everything in terms of linear algebra. Just keep in mind, though, that when I'm talking about space, I will be talking in this discussion about vector spaces, but in general, check cohomology can work in any topological space. The best way to understand check cohomology is by looking at an example. For our example, we're going to look at a data set X which only has 8 points and lives in two-dimensional space. Check cohomology can be done with any dimensional space. However, if we're looking at practical things, usually we won't need to go beyond the third dimension. The first thing we're going to want to do when we're computing the check cohomology of a dataset is we are going to want to center disks of some positive radius around each data point. Now, in this example, I used a disk of radius of 1.5 units. You could use any radius you want. Just note that your answers will vary as you change the radius. And by that, I mean if you have more intersections, generally what happens is you don't notice as many holes and loops and gaps. You start to lose that information. And if you make the radius smaller, you start to have gaps and loops that weren't there originally either. Neither of these options is inherently better or worse, but it is worth noting that you can sometimes drastically change the outcome of this process just by adjusting the radius of these disks. Next, what you're going to want to do is you're going to want to take a note of all the disks that you used, and you're going to want to note their intersections as well. Now, here we had 8 data points, so we know there's going to be 8 disks. I labeled them U1, U2, U3, and so on. And for intersections, we denote the intersection of U1 and U2 by U12. We denote U2 and U3's intersection by U23, and so on. So once we've done the counting up of all the disks and intersections of disks, we're ready to build what's called a check complex. For our purposes, a check complex is going to be a sequence of vector spaces connected by linear maps. It starts at the trivial vector space and ends at the trivial vector space, but it's what's in between that we care about. Now notice our first non-trivial vector space is R8. Well, notice we used 8 disks. Our first non-trivial vector space always corresponds to the number of disks we used. And then the vector space following that is representative of how many pairwise intersections we've had. So we had 8 pairwise intersections, so we go from R8 into another R8. Notice we did not have any threefold intersections. So once we're done with the pairwise intersections, we can map back to the trivial vector space because there's nothing left for us to count up. So we have our check complex in place. This allows us to find what are called the cohomology groups of our data set. These are what tell us about the structure of the set. This is where we learn about the holes and gaps present in the data set. There are infinitely many cohomology groups. It starts at 0 and continues on through all of the positive integers. But for our example, we only need h0 and h1. h0 is going to tell us about how many clusters of data points are present in our data set. This corresponds to finding the gaps in the data set, because say you have a big cluster of points on the left side of your data set and a big cluster of points on the right side with nothing in between. That gap between all the data points is going to be reflected in h0. h1 will tell you about the loops, two-dimensional loops that is, present in your data set. This corresponds to finding holes in your data set, because if your data points are arranged in a sort of circular shape, there's something missing in the middle there. And for the higher cohomology groups, they just tell us about higher dimensional loops that might be present. So H2 would tell you about three-dimensional loops, H3 would tell you about four-dimensional loops, and so on. Now, it's up to whoever provides us with this data as to what the presence of these gaps and holes actually means, but the fact that we can find those gaps and holes is very useful to researchers. So the Pth cohomology group is just a general cohomology group. I cannot easily define it without using any topology, but I can give you a formal, informal definition by this thing down here. So the Pth cohomology group, HP, it depends on C bullet. C bullet just represents our check complex, because remember, if we change the size of our disks, we change what our check complex looks like. And if our check complex is different, then it turns out that our cohomology groups can also be different. So it does depend on which check complex that we are using. But I'm just going to refer to them as H0, H1, and so on. HP is isomorphic. That just means it looks like Rn. So some vector space Rn, where n is not just any number, but the particular number given by taking the dimension of the kernel of the map delta p from our check complex and subtracting from that the dimension of the image of delta p minus 1. So to find h0, given our check complex, we're going to need to look at the dimension of the kernel of delta 0 minus the dimension of the image of delta negative 1. Similarly, for h1, we're going to want to look at the dimension of the kernel of delta 1 minus the dimension of the image of delta 0. So before we can actually find these cohomology groups, we need to know the dimension of the image of delta negative 1, the dimension of the kernel of delta 0, the dimension of the image of delta 0, and the dimension of the kernel of delta 1 as well. So the good news is we can find two of these things right off the bat just by thinking carefully about the maps in our check complex. If we look at delta negative 1, we see it goes from the trivial vector space into R8. Now, the image of delta negative 1 is the stuff in R8 that maps over through delta negative 1 from the trivial vector space. But the only thing we can send over through delta negative 1 from the trivial vector space is 0. And since delta negative 1 is a linear map, 0 in the trivial vector space maps to 0 in R8. So in other words, the only thing that can be in the image of delta negative 1 is 0, and therefore the dimension of the image of delta negative 1 is also 0. Now, there's a similar trick we can use to figure out what the dimension of the kernel of delta 1 is, and it's a little easier to understand. Delta 1 is mapping from R8 into the trivial vector space. So it's mapping everything in R8 to 0. In other words, everything in R8 is in the kernel of delta 1, so the dimension of the kernel of delta 1 must have the same dimension as R8, which is 8. This doesn't tell us what the image and kernel of delta 0 look like, and we need to know that to find their dimensions. What we would have to do is make a matrix to represent the function delta 0. We would have to then reduce this matrix to find the rank of delta 0, which would give us the dimension of the image of delta 0. From there, we could apply the rank nullity theorem to find the dimension of the kernel of delta 0. But all of that is a lot of work and very time consuming. We don't have enough time for that, but since this is a pre-recorded lecture, I will scroll through those slides so that you can work through it on your own if you're really curious. Remember that H0 is more or less in the form of the vector space Rn, where n is a particular number given by the dimension of the kernel of delta 0 minus the dimension of the image of delta negative 1. Now, if we had done the matrix work with delta 0, we would have found that the dimension of the kernel of delta 0 is 1, and we did discuss that the dimension of the image of delta negative 1 was 0. So n in this case is going to be 1 minus 0, or just 1. So h0 is going to look like R1. Now, similarly, we can find h1 very much the same way. We did know that the dimension of the kernel of delta 1 was 8, and the image of delta 0 had a dimension of 7. h1 is in the form Rm, where m is the particular number given by the dimension of the kernel of delta 1 minus the dimension of the image of delta 0. So m corresponds to 8 minus 7, which is just 1. h1 is going to look like R1, just like h0. So what does all of this mean? Well, h0 being 1 means that there is one cluster of data points. So all of our data points are grouped together, there's no separate pieces. So there are no gaps present in this data set. Now, h1 being 1 implies that there is a two-dimensional loop present in the data set. This means that there is a hole present in our data set. There are no gaps between the points, but they do form some kind of hole. Now, if we look back at our shape, I drew in some dashed lines so you can see that it's a very circular type shape. The hole we're talking about is this stuff here in the middle where there are no data points to fill things in. So yes, we can see these points are relatively close together, and we have this nice circular pattern creating a hole in the center. The structure of our set certainly reflects the cohomology groups as expected, so that's how we know we haven't made any errors. So we're almost out of time, but just some last words on this subject. Turns out we could have used squares instead of disks to cover our data set, and in fact, check cohomology would allow us to use any shape of our choice. It just has to satisfy certain conditions for contractibility. That's a topology thing. For 2 dimensions, you can pretty much say any polygon is safe to use, as long as you only consider the area of the polygon and not the perimeter of the polygon. You can see in this figure there are plenty of other shapes we could use. We could use the octagon, the triangle, or the dinosaur shape, and we would still get the same cohomology groups. So squares are actually better than disks for determining higher numbers of intersections. When I say this, I mean in terms of making an algorithm to automate this for us. We didn't have time to get into this, but if we really want to use check cohomology, we're going to be working with a lot more than 8 data points, and that's going to take a long time if we try to do it by hand. So we want to automate the process as much as possible. That being said, when it comes to algorithms, it's very difficult to determine when 3 or more disks all meet in one point, whereas with squares, it's very, very easy to determine when any number of squares meet at a point. And with that, I thank you for watching, and I hope you enjoyed.